Hello. My name is Constantine Murenin, and I'm currently a student, a master's student at the University of Waterloo. And I'm going to give a talk about the history of the OpenBSD hardware sensors framework. So I originally started working on the hardware sensors framework when I was an exchange student at the Montfort University in England. So the talk will consist of introduction. We'll then describe framework API and utilities that we have in OpenBSD for interfacing with the sensor framework. I will talk about drivers, about IGC BASCAN, and I will conclude the talk with a conclusion. So first of all, what is a sensor? Well, a sensor is any device with a sensor-like data. And sensor-like data can include temperature readings, voltage readings, fan speed, and it can also be logical drive status for RAID disk. And in OpenBSD, we can also have a sensor as a time offset of the local clock against some external clock source, like GPS, for example.
What about like
radio?
Accelerometers or
Yes, accelerometers also. I couldn't install the types here because I think there's about 18 types, 18 different types. So other sensors are they common at all in the modern computers that we have? And many super I/O chips that desktops have, for example, they feature an integrated hardware monitor logic. And those chips they allow you to monitor the temperature, the voltage from the power supply line, and the fan speed. And recent processors, they also have public documented interfaces for acquiring temperature readings. So for example, Intel 4 and Core 2 processors, they have this, and some new processors have it too. And AMD K8 and K10 and K11 also have it. And IPMI servers and ACTI laptops also provide you with different readings, temperature readings, voltage readings, also intrusion, like cover. If you open the cover of the server, then it shows the exact type. And SCSI enclosures, they also provide you with different sensors. And 10 gigabit Ethernet cards, because they run pretty hot, they also have temperature sensors. And 802.11 wireless devices often have temperature sensors. So why sensor framework? Well, monitoring environmental values can predict, detect, and troubleshoot system failure. So, for example, if the fan fails, then if just one fan fails, then the system will still run fine. Because, for example, just an additional fan if you have many fans. But if too many fans in the system fail, then the whole system may overheat. For example, the CPU clock may be decreased automatically to prevent damage to the CPU when the system runs slow. And with a unified interface, as we have in OpenBSD, and no configuration required, so the framework works out of the box, right out of the box. It's really easy to use. And lots of sensors are fun. Like it's always pretty interesting to, for example, compile the kernel and watch how your temperature sensors go to the top. So in OpenBSD, just to give you an idea, we have some temperature sensors that are absent from other systems. So for example, SG10, it was written by Fyodor some time ago. It provides temperature sensors for sodium memory modules. And we also have the temperature sensor for AMD family 10H and 11H processors. It includes Phenom and Phenom 2 and Turin X2 Ultra and other new processors. And the interesting thing is that both of these drivers, they are still missing Linux. So, and this is how the SD10 temperature sensor was written. There is actually, at the time that it was written, there were no productions. There were the memory modules that contained the temperature sensor. They were not yet available on the market. So what Peter did is he ordered these temperature sensors, and he soldered them on a board. And then it turns out that the easiest way to connect these temperature sensors to the motherboard is by using a memory module. The I2C is by using a memory module. Because memory modules, they have SPD chips, which allow you to detect the different settings of the memory, so like the refresh latencies and stuff like that. And it was easiest to access the I2C bus by using the memory module. So this is another picture of the chip, the temperature chip routed to the memory module. So design decisions. In OpenBSD, the design decisions regarding most of the functionality is to keep it simple, secure, and usable. And it should also work by default. So if the feature requires a lot of fiddling around with different configuration options or reading too much documentation before you can do anything with the stuff, then it's not really our thing. And over-engineering of many of these parameters would be useless because many devices, they have incomplete specifications. So it's not always possible to write drivers which would allow you to utilize all of the features of the device. And we also don't like knobs in OpenBSD. So we don't provide any much of a configuration option for this temperature sensor. They just work by default, and you can look at it, and it just works right after you install OpenBSD. And I'm going to give an example of how voltage sensors work to give you some idea about why over-engineering is kind of useless. Most chips, they have sensors, they have voltage sensors, they can sense voltage from 0 to 4 volts or from 0 to 2 volts. And excess voltage is removed by resistors. So if you want to monitor the 12V power line of the power supply unit, then you just need to remove the excess voltage by resistors to bring it to around 3 volts. And then chip manufacturers, they provide resistor recommendations. And apparently those resistor recommendations, they're not always followed by the motherboard manufacturer. And here's an example, here's an illustration of how this stuff works. So the original reading on the sensor, it could be, say, OXCD in fact, or 203 in decimal. And then if we want to get the actual voltage from this value, from this register reading, we have to multiply it by 16 millivolts because we have the scale from 0 to 4 volts. And then the actual reading then is 3.24 volts. And then if we know that this sensor, it actually, through resistors, it's actually reading the reading that it provides is actually goes for 5 line, then we multiply it by a resistor factor. And the resistor factor can be, for example, 1.68. And then we get the reading of 5.34 volts. Or if it's if we need to scale for 12 volts, then we multiply it by a different resistor factor. And then we get, say, 12.31 volts. So in this context, it depends if motherboard manufacturers, they provide like which sensor is supposed to use by which, for monitoring which power line. But it is up to the motherboard manufacturer to follow those recommendations. And it is up to the motherboard manufacturer to use the correct resistors. So these resistors, they are often ignored by motherboard manufacturers, or sometimes they even absent from documentation for certain chips. And the result is that voltage doesn't really scale, and we have to do the best with what we have. So Framework API. Framework API is defined as sys sensors.h, and there are two data structures, struct sensor and struct sensor.det. And the transport is done via sysctl 3. And in struct sensor, we have sensor description. For example, it could be CPU or external, internal. And sensor description is optional. So if you don't know what the temperature sensor is used for, then you shouldn't, when you write in the driver, you shouldn't provide any description for the sensor. There's sensor type in unit or unit, and it can be, for example, temperature and voltage, indicator, drive, and delta, and there are a lot of other types. And in the proceedings with the table of all types, you can take a look at it. And sensor state can be unspecified, can be OK, warning, critical, or unknown. And again, many of these, for example, Super I/O sensors, they don't have any notion of sensor type. So those drivers, if you don't have any notion, then the sensor type should be unspecified, because you don't want to confuse the users into thinking that a certain sensor has an OK state where you actually don't know what the state of the sensor is. And this is an example of how you add sensors in drivers in the attach procedure. So you first initialize the X name of the sensor dev structure. Then you have a loop where you initialize the type of each sensor. And then you call the sensor attach function to attach the sensor to the sensor dev device. And this is just an example of the minimal driver. So you can initialize many more fields. This is the minimal driver for, say, some temperature sensor over some Super I/O. And after that, you can call the sensor task register. And refresh is the name of the function which does refreshes for you. And pipe is the argument, which means that the refreshes, that function refreshes will run every 5 seconds. And afterwards, if all of the previous steps succeeded, then you call sensor dev install. And sensor dev install makes the whole tree of this driver available in sysctl. And this is an example sample refresh procedure. So in the refresh procedure, you just update the value of each sensor. And you can, of course, update some other fields to help. Basically, this is the example of the system driver. So sensor tools in OpenBSD. We have quite a number of tools. And originally, when the framework was first appeared in OpenBSD, it was only possible to use sysctl 3 and sysctl 8 to query sensors. But right now, as you can see from the slide, we have quite a number of utilities. So sysctl has a sensors display, which allows you semi-real-time sensor monitoring. So I'm sure everyone is familiar with sysctl. So it works similarly for the sensor displays instead of for other displays. We have a sensor monitoring daemon called sensor_t, which allows you to monitor sensors and provide alerts if some values go out of range. We have ntpd, it's time delta minimizer. Time delta sensors, it provides you time offset from your local clock against some external time source, which can be a radio station or it can be GPS. And snmpd, which is an SNMP daemon. We also have in the ports tree, we have a utility called symon. It allows you to monitor sensors from many different machines and collect the data on one machine and then make graphs with MRTG. And recently also GK realm was added. Sensor support for GK realm was added. And GK realm, it provides you GUI monitoring for the sensor. So this is an example of how it works. So after you install OpenBSD, the sensor is already configured, so you don't have to reconfigure anything. You just basically install OpenBSD, you just put it, and if it's a regular desktop, then it's very likely that you will have some sensor. So at the very least, modern CPUs, they have a response sensor. So if you have an AMD Phenom processor or AMD Turing processor, then you will have a sensor. Or if you have an Intel processor, Intel 8, Intel 4, i7, I think too. So you can see here in the display that there are two sensor drivers, one called KM, and another one is IP. And KM is the sensor driver for AMD Phenom processor. Then you can see that it has one temperature reading, which runs at 50.5 degrees here. And then the IT driver, IP4 driver, is a driver for Super I/O IT tag Super I/O devices. And in this example, you can see that it has 3 temperature sensors, which is kind of incorrect. And then it has one fan sensor and several voltage sensors. And sensors_d, it's a monitoring daemon, and basically it fills in your logs with different changes in the sensor ratings. And no manual configuration is required for sensors_d for smart sensors. So if you have, for example, in your server, if you have IPMI, IPMI provides status for all sensors. So every sensor, if the status changes from say OK to critical. So for example, one of your sensors is broken and the status changes, then sensor D will automatically log that in logs via syslog. And for those sensors that require, that don't keep their state, very minimal configuration is required. So for example, you can say configuration file 10, low equals 15C, and high equals 65C. And then every time the temperature sensor, any temperature sensor will go below 50 degrees or above 65 degrees, or will go between 15 and 65 degrees, then an alert will be generated inside log. And you can also specify a command which will be executed if the values change. So, and you may think like, why do you care if the temperature sensor will go below 15 degrees centigrade? And actually you do, because there's been some research done that if you freeze the memory module, then you can actually take the memory module out of the computer, and the contents of the memory can be preserved for a certain amount of time. And if you freeze the memory module low enough, then it can hold the data for several hours. And then someone can just freeze your system and take the memory modules with them, and then recover some of the passwords that are stored in your memory. So you actually do want to monitor for both the high and for low changes in the memory modules. So drivers. Drivers can be roughly divided into Super I/O hardware monitors, which include, for example, LM4, IP4, DAN, Nagios, NSC, LTC Geo, SINS, SCH Geo, and some others. And also some BIOS hardware monitors. And there are too many to mention. There's around 29 drivers that do monitoring their interfaces via some BIOS. Then there are some embedded temperature sensors in the Ethernet chips, for example, 10 gigabit Ethernet chips, or in CPUs from Intel and from AMD. Also SCSI enclosures and IPMI and LASN. And there are various ACPI sensors which allow you to monitor temperature, voltage, and power, battery information. And rate logical drive status sensors, and time offset sensors, and other sensors. And in this pie chart, you can see the distribution of all of the different sensors by their primary category. So you can see that the majority of the drivers are I2C drivers. And then the next one, and this pie chart is for OpenBSD 4.5. The latest release, which will be released this May, officially released this May. And you can see that the I2C, they form the majority, and then drive sensors follow with Super I/O sensors and other sensors. And miscellaneous sensors they include IPMI and some others. And from this chart, you can see the distribution of drivers by type. And you can see that, for example, 49 drivers, they use temperature sensors. They provide temperature sensors, exposed temperature sensors. 25 drivers expose fan sensors. And this list is non-exclusive, so some drivers they expose both temperature, fan, and voltage sensors. And you can see that the most popular type that sensor drivers expose is the temperature sensors, and 49 drivers expose the temperature sensors. And then the next one is the fan and voltage sensors, which are exposed by 25 drivers. And then afterwards, you can see indicator, raw sensors, and drive sensors. And drivers by release. So with OpenBSD 4.5, we have 72 drivers using the sensor framework, exposing sensors to the sensor framework. And you can see that originally started with OpenBSD 3.4. And for those of you who are not very familiar with OpenBSD, basically we have, every year we have exactly 2 releases. So it's been over 10 years now, I guess, since we've had it. 5 years. So originally with OpenBSD 3.4, there were only 3 sensor drivers. And then, as you can see from this graph, it grew really heavily with OpenBSD 3.9. And that's when the I2C framework was heavily redeveloped, and a lot of I2C sensor drivers were introduced. And afterwards, it's been roughly from around 8 drivers, I think, on average, every release. So in the previous release, there were 68 drivers, and right now there's 92. I think that's because of the slowdown in the economy. So I2C. I2C bus generally lags many chips on I2C bus. They lag minute-full signatures, and Open Firmware provides a list of devices, a list of pairs of strings and I2C addresses. So basically, on a regular system, you have to query each device on the I2C bus. It has 256 registers, and many manufacturers, they have different registers which signify which chip it is. So one manufacturer may have a register 0805, which provides you with the name, with the model of the device, with the number of the device. But another manufacturer can have a different register which provides you with the name of the device. And it means that it's very difficult generally to decide which device you have, because there is no standard saying which register you should look for to find which device you have. And those architectures that have Open Firmware, Open Firmware provides a list of devices as pairs of string and I2C address. And drivers matched by string. So, for example, ADT 7467 is a string provided by Open Firmware, and some driver will use this string to decide if it supports this device or not. And on those architectures where there is no Open Firmware, for example, on i386 and i364, we have a code in sysdev I2C scan.c, which goes through a list of I2C addresses where transfer leave on the system. And for each address, it scans the value of each register, and it caches the first read of that register. Unless this value is ignored, unless this register is ignored entirely, we get blacklisted. So, for example, some chips, they are known if you access certain registers on some chips, then the whole system may freeze. And in order to guard against that, there is a blacklist of those chips. And the result of successful scan iteration is a string describing the chip. So, for example, it can be for some Win1 chip, the string can be W83 792G. And the drivers, because the interface of I2C slave devices is the same between all architectures in FreeBSD. Drivers on both Open Firmware architectures and on non-Open Firmware architectures, they match just by string. But on Open Firmware architectures, we use more reliable data from Open Firmware to detect which sensors we have in the system. Whereas on architectures which don't have Open Firmware, we have to look through different sets of registers ourselves and decide which chip resides at that specific address which we're looking at. So all signatures are located in I2C scan.c, ensuring that there are no conflicts on those architectures that don't have Open Firmware. And we did this, of course, all of it OpenBSD way. All of this is enabled by default. So when you boot the system, it just works, and code is tested on all machines that have I2C and don't have Open Firmware. And all supported I2C drivers are enabled in generics and just work. So if you boot the machine, you will just have a lot of I2C drivers, I2C sensors, and you can have a lot of I2C sensors. And one thing we do in I2C scan.c is we print a register dump for unidentified sensors into DMS. And we kindly ask users to voluntarily send DMASks to our archive at dmask@openbsd.org, which is a private archive, which is an archive accessible by OpenBSD developers only. And we have this archive to ensure quality assurance. So every now and then, every developer looks at this archive and sees which devices, which hardware people are running OpenBSD at, and which devices are supported and which devices are not supported. And we use this archive to also add support to some devices which people have, but which we don't have drivers for. And this register dump, this I2C register dump, can also be used to write a sandbox driver wrapper, which would parse those dumps and which would load the driver in the userland. And you can test the driver in the userland. Basically, can convert the driver from being a kernel driver to being a userland driver. And you can test the driver against that I2C dump. So if you want to develop your driver, and you don't want to, you don't actually have a physical access to the hardware, then you can use it to do the sandboxing. And in the paper, I describe how you do the sandboxing. So you can take a look at the proceedings if you're interested in that. And the sandboxing, it also streamlines, it obviously streamlines I2C driver development and eventually testing. And we've had, I think, 2 drivers written the sandboxing. And I wrote one of the drivers, and I committed it, and then I asked the person if we had the hardware to test it, and he tested it, and it just worked right from the start. So it simplifies a lot of things. So originally, OpenBSD hardware sensor framework, it was based on some drivers which were part of NetBSD. And NetBSD's framework is called ANSYS and Simon. And the difference between OpenBSD and NetBSD framework is that OpenBSD has many more I2C sensor drivers. So most of the I2C, if your computer has some interesting I2C sensor chip, then most likely than not they are supported in OpenBSD. So you just boot OpenBSD and all of those drivers may just appear in sysctl with sensors. Whereas in NetBSD, you have to know which addresses, which address the sensor device is located at, and which sensor device it is. And you need to manually enable the drivers using that specific address so that it works. And because of that, because it's so complicated to use I2C drivers in NetBSD, not that many drivers were written. And overall, the API is more complicated than the one in OpenBSD. And the tools that are provided for sensor monitoring in NetBSD, they're not the standard tools as in OpenBSD. So for example, in OpenBSD, you can use SiteStat to view real-time, take a real-time sensor monitoring. And as I mentioned, I'm sure everyone is familiar with SiteStat. So it's pretty easy to use. Requires very little additional learning. And drive sensors, they were ported to NetBSD from OpenBSD some time ago. And NetBSD also has several redesigns of the framework and of their YANSYS framework. And in 2007, YANSYS framework was YANSYS 2 framework was introduced. And some API resembles the API that was introduced in November. It increasingly resembles OpenBSD Center Attach API. So framework timeline simplified. Basically, the YANSYS and Simon, they were introduced to NetBSD in 1999 or 2000, and originally had LM4 and the YANS driver. Then in 2003, Alexander Yurshenko, he ported the LM4 and the YANS driver into OpenBSD. But instead of porting the framework, he designed a much easier sysctl-based framework. Because actually, the NetBSD documentation for YANSYS, it said that YANSYS should be replaced by sysctl interfaces should long be developed. And LM4 and the YANS, they first appeared with simpler sysctl-based interfacing in OpenBSD 3.4. In 2004 and 2005, there's been a lot of work on the sensor framework. And Alexander Yurshenko, David Wayne, Mark Katniss, and Peter Robb implemented a lot of features. So, for example, David Wayne introduced the sensor task procedure, and then Peter Robb, he wrote the I2C scan procedure, and a lot of drivers, a lot of I2C drivers. And of course, a lot of people wrote different drivers. So we have 72 drivers right now. And it wouldn't have been possible without everyone else who wrote the drivers for this framework to be as popular as it is right now. So in 2006, I have finished converting. I finished my patch for converting the sensor framework from one-level addressing to two-level addressing. So previously, the sensors were addressed by HW.sensors and then the numerical number of that sensor on the machine. So, for example, you can see here that the third temperature sensor on the LM0 device was previously numbered, could have been numbered as HW.sensors.11. And after this patch, after it was committed, the addressing scheme was changed to HW.sensor.0.10.2. And then in 2007, I participated in Google Summer Code. To port the framework to FreeBSD. And in 2007, in September 2007, the final patch was released for FreeBSD 7.0 current. And it has been committed. It has been committed to DragonFly BSD, and then it has also been committed to FreeBSD. And has been then back out of FreeBSD. So, and it has been back out of FreeBSD because Paul Henning Kemp, he objected to certain features of the framework, and his most objection was that sensor drivers, they shouldn't be in the kernel per se, but then some sensor drivers which are actually present right now in FreeBSD, they are actually in the kernel. For example, there is a K10 driver which allows you to monitor the chips on AMD K processor. And there is a Core 10 driver which allows you to monitor the temperature values in the Intel Core processor. So this talk is only 45 minutes, so I think there's no time to go more into summer code. And I'm going to go to conclusion. So right now we have 72 drivers in OpenBSD 4.5, and the framework is very popular and in high demand. And driver code is shared between NetBSD, OpenBSD, DragonFly BSD, and FreeBSD. So for example, the Core 10 driver was written by Ruud Paula for FreeBSD, and it has been ported to NetBSD, and I also ported it to the central framework during the Google Summer Code that I did, and it was also committed to DragonFly BSD. And some other drivers were ported from NetBSD to OpenBSD, and others were ported from OpenBSD to NetBSD. And generally, some drivers are shared by all four systems, I think, or at least some combination of three systems. And usual interface of the framework is compatible between OpenBSD and DragonFly BSD, and patched FreeBSD. So, for example, sensors D, you can take sensors D from OpenBSD 4.5, and you can put it into DragonFly BSD, and it's just going to work. Or you can apply the patch, which was released after summer code, to FreeBSD 7.0, or I think it still applies to 7.1, with some minor conflicts in the make files. And you can put sensors D, you can use sensors D on that system too, and it's going to work. So future projects can consist of writing even more sensor drivers for OpenBSD. And I originally, the last time I gave this talk, I projected that it could be 75 drivers by OpenBSD 4.5. But at OpenBSD 4.5, we would have only 72 drivers. And that can be attributed to slowdown in the economy. So the next estimate is 76 drivers by OpenBSD 4.6. And another interesting project could be porting the sensor detect.pl from LM-sensor. And sensor detect.pl is a Perl script that runs through I2C, I2C devices, and for devices on the I2C bus, and it detects which devices, which chips are represented on the bus. So basically, it allows you to see which chips you have on the system. And it can be helpful if you want to port drivers from, say, OpenBSD to DragonFly BSD, or from OpenBSD to FreeBSD, or from different systems. Sensor detect.pl, it can tell you which chips you have on the system. So it's easier to code those drivers. Or for example, it also allows you to detect which super I/O chips you have. So if you want to port some driver from NetBSD to OpenBSD, from OpenBSD to NetBSD, then if sensor detect.pl is ported to BSD, then you can see which chips, or you can ask users to run sensor detect.pl to tell you which chips they have, so that you can write the drivers and let them test the driver. Another interesting project is porting out sysctl to FreeBSD or DragonFly BSD APIs. And yet another project is improving in SensorD. So SensorD has been improved in I think in 4.3 and 4.4, but it still lacks some interesting functionality. And in the paper, I described some of the functionality that it's lacking. And one of the most interesting topics that I was personally interested in originally when I started working in this framework back at the University is time-speed controlling. So for example, on desktops, you have a super I/O chip, and it allows you to control the voltage that is supplied to the fans to the fans. And then it's very often, if you have, for example, some motherboard, like if you buy just components and you assemble the computer yourself, then it's very often that the fans will be very noisy. And in older motherboards, it wasn't possible to actually, the BIOS didn't provide you with any options to actually have, to actually control the speed of the fan. But very often the control is still possible. You can actually still change the registers on the chip, and the chip will provide different voltage to the fans. So you can run the fan at, say, 40% voltage, and then 40% voltage will be around 5 volts, and it will make the system less noisy, and you can still put the voltage onto a higher value if you want the temperature, if the temperature goes up, and if the temperature goes above a certain limit. And the chips, they actually have too many different interfaces to allow you to do fan controlling. So the fan controlling can be done on the chip itself. And some chips, they provide 5 different levels for, so basically you can specify 5 different voltages that will be supplied when 4 different temperatures are crossed. And the interface for fan controlling would really be complicated. So if it's going to be released, it's probably going to be released as a separate patch. It's not likely at all to go into OpenBSD, because in OpenBSD we like all the things to be simple. And such interface, it really doesn't sound like it could be made simple, because there are just too many options to do that controlling. So this is the end of the talk. Are there any questions or comments? Yes?
How often the time span it's sensing?
I'm sorry?
How often the time span it's sensing?
How often the
time delta, the delta.
is it the question about time delta sensing?
No.
About refresh?
Time between calling.
What time between calling? It's usually, most drivers do it, each driver specifies the time. So in that example, you can see that it was 5 seconds when you call sensor task register. Then you can specify for the update procedure to be run every 5 seconds. And usually the chips themselves, they update the data only every 1.5 seconds, I think. So if you try to query it too often, then I think certain chips, they may not have the time to actually refresh the data. Or if you query it more often than 1.5 seconds, then there's just no need to query it so often, because you aren't going to get any new values, because they update it only every 1.5 seconds. So did that answer your question? Was it the question that you asked that we answered? Did I answer the question? Any more questions?
Okay, so when you are reading the values from user space, it's always by forward. There's no asynchronous notification of changes.
Right.
So is there any way you can synchronize your polling from user space with when the values are updated? I want very fresh data. So I don't want my data to be 5 seconds old. I want it to be 10 milliseconds old, and I get the latest value.
Currently, it's not possible because we don't provide you with the time when well, actually, the time that, for example, when we deal with time delta sensors, then time delta you can specify in the sensors the time that the sensor was updated, and it's currently used only for time delta sensors.
Okay, that's useful. That would at least solve part of the problem.
Yeah.
Okay.
So you would need, for example, for time delta sensors, I guess you can take a look when the value was last updated, and then you can use the knowledge of how often time delta sensors run the update procedure.
And all the other sensors are updated on the same schedule.
No, every sensor it updates on a different schedule.
Yeah, if they have timestamps attached to the values, that would be nice.
Yeah.
I think that what you're asking is a little bit outside of the specification of what we're trying to do. This is not a high availability interface. This is an informative interface. So, for example, I run a cron job that looks at a couple of my sensors for a couple of machines in my machine room, and
Sure.
when things go bad, it sends me a mail anywhere in the world.
Right.
And when things go even worse than that, it starts alerting every single person in Calgary who has access to my house. Okay, and when things go even worse, then it starts powering things off. I mean, those type of things don't require second-to-second accuracy.
No, they don't.
Yeah.
They don't.
We also have to remember, for many of these I2C chips, the ACPI in the machine is actually also involved in the process of dealing with these things.
Yeah, and then all bets are off, right?
Yeah. So even if we look at some of these chips and we start getting really deep down and try to access them and use their features to the full level, we're starting to interfere with ACPI. So all the issues that you worry about with SMP kernels, you got the same thing happening again. You're dealing between the code you're writing yourself and a completely unknown system that is configuring these chips and changing them and doing who knows what. And there's a dedicated interrupt line coming down the I2C bus, which causes a non-masterful interrupt on the CPU, jumps it into BIOS code running in SMI mode, and then who knows what it does. So really scary stuff. So that's why we specifically try to do the minimum when it comes to I2C chips.
Yeah, it's very good.
Nice comment from the audience.
Yes?
I tried to port I2C scan to an ARM platform that I had running FreeBSD, and it had a number of EEPROM chips on it. And one of the problems, if you go and poke random addresses, was that I would discover contents of the EEPROM were randomly changing when this happened. When I would run the scanning program. How do you deal with this in normal systems? I mean, the system I was on was kind of funky because there were like 12 of these I2C devices that were EEPROM.
On one I2C bus?
Yeah.
Okay, that's electrically not permitted. So there you go.
Actually, it is electrically permitted.
12 I2C EEPROMs on one I2C line?
Yes.
The spec is for 10.
Wow. The hardware guys said it was fine.
Wow. Yeah, so almost all those probably are going to be the I2C bus master driver. And yeah, we have the same problem. We have buggy I2C bus drivers like crazy too, and it drives us
The issue is you talk to the EEPROM and you try to read a register, but for the EEPROM, that really writes a location.
Because the I2C protocol went buggy.
No. Absolutely did not get corrupted.
Yeah.
This would also happen if I took half of the cards out of the system as well. It had to do with where the particular I2C EEPROMs were on the I2C bus.
They weren't in the standard defined place.
There is no standard defined place.
There is a
for
standard
I2C,
defined place.
For I2Cs. They could be in a number of different places, depending on whether they're 8-bit or 16-bit technology.
So I2C scan, as we coded it, specifically only scans for sensor chips in a space that's reserved for sensor chips. So if somebody goes and puts something else in that space, yep, you're going to read it. And it's unavoidable. So our I2C scan code currently works on everything except for two machines. There's a Sony VIO that the minute we read from the I2C bus, our very first read operation resets the machine.
Nice.
Okay? I mean, we're not even reading a register, and it doesn't matter what register we read. As soon as we access that I2C bus, it's like they've wired the I2C read line to the reset line of the CPU. Okay? And there is some unknown chip, which is mounted as a temperature sensor on an ASUS motherboard, which one of our developers in Russia has. And we don't know what chip that is. He can't see it, but he knows that's the I2C chip because he traced the wires to there. And whenever we read any of 20 registers from that chip, and it's in a very well-known location where all the LMs land.
Right.
When we read those 12 registers sequentially, the machine locks up. So this is buggy hardware as far as we're concerned, considering that we've only found 2 cases.
Yeah,
that's acceptable losses.
Yeah, the other problem, and this may have been a quirk of the I2 EEPROM, that for a 16-bit, if you only send 1 byte to read the 16-bit thing, it will lock up the I2C bus because it's driving the line,
That's right.
waiting for the response, or waiting for the right things to come in. So
Yeah.
that was the other problem that I hit when I was trying to do this.
Yeah. Those devices are not very common in PCs.
Yes.
So we've gotten away with it.
Yeah, I can believe that. This was a system that had a number of removable cards that we used the I2C to identify the card when it was plugged in. So we know, oh, this needs 12 volts, this needs 6.5 volts or whatever. We turn the cards on and off.
Can you write your own scanner?
Well, we would just disable it and hardwire each of the devices to a particular location we expected. That's what we wound up doing. So. But yeah, the EEPROMs scare me.
They do scare me.
Any more questions? Well, I guess we can conclude the presentation. Thank you very much.